In this segment, we'll talk about four vectors and covariance. So first of all, let's ask ourselves a question. What is it that makes a vector a vector? So you could say, okay, you take a few numbers and put them together, and you got yourself a vector. But having a few components is only a small part of what it means to be a vector. Now we usually think of vectors in terms of arrows. Now the essential part of being an arrow is that we know how the components of an arrow transform as you rotate the reference frame. So we can start with some reference frame with some axes x, y, and z. And then, let's say, in this reference frame, we have a vector with components v1, v2, and v3. So we're dealing with 3 dimensions here. Now, you take the same vector and you want its components in some other reference frame that is rotated with respect to the first one. So the rotations form a orthogonal three-dimensional group, and then those rotations can be represented in terms of matrices that depend on the axis with respect to which you rotate and the angle. So those are the parameters of the rotation, or you can specify it using Euler angles. Either way, there are 3 components. And then those matrices act on 3-dimensional vectors. So then we know that we can write that the components of the vector in a new reference frame will be given by the rotation matrix applied to the old coordinates. So we could say that a vector is a collection of 3 numbers that transform just like the components of an arrow do under rotations. So these matrices are those matrices that affect the rotation of the arrow, and then anything that transforms according to this law is a vector. This is a complete definition. Now, the rotations themselves are elements of the rotation group, and the rotation group is the one that leaves the sum of squares invariant. So it's the same no matter how you rotate the reference frame, because it's just the length of the arrow, v squared. Now in special relativity, we're dealing with 4-dimensional spacetime and transformations that mix time and space components together. So Lorentz boosts mix time and space coordinates. You can also have pure rotations that only affect space. Those are just like the rotations we discussed before. Now what we know about these 4-dimensional rotations is that they leave the square of the interval invariant. Now remember, the interval is defined as ct squared minus x squared minus y squared minus z squared. That gives the interval separating the given point in 4-dimensional spacetime from the origin. Now let's adopt the following convention. So let's write ct, x, y, and z as a set of 4 numbers. And we'll denote it as x alpha. Alpha here is a superscript, and it has 2 notational functions. So the first function is that alpha is an index that goes from 0, 1, 2, and 3. And then by definition, x naught is ct, x1 is x, x2 is y, and x3 is z. So alpha is an index labeling the elements of this four-dimensional object. But also x alpha, written separately, is also understood as a whole collection of four numbers. So instead of writing x with an arrow, like we do in 3 dimensions, here we use this notation x with the superscript alpha. Now, this notation will be called contravariant, or alpha is a contravariant index for reasons that will become clear later, and then it appears on top, x superscript alpha. Now, in addition to these components, we'll introduce a different notation with a subscript, x sub alpha, and it looks the same, but the spatial components have an opposite sign. So this is called a covariant index. And then we'll define what's called a contraction. We'll write x sub alpha, x superscript alpha as ct squared minus x squared minus y squared minus z squared. So x sub alpha and x super alpha is just a sort of an inner product. So just like we write in 3 dimensions, v times v is vx squared plus vy squared plus vz squared. Here we multiply the corresponding components of contravariant vector x super alpha and covariant vector x sub alpha. So I've introduced a new term, covariant and contravariant vectors. Those are the collections of these 4 numbers. So why do we call it a vector? Well, this quantity here that we have defined, so this is nothing other than s squared. So this is an invariant. So Lorentz transformations, including rotations and boosts and any combinations of those, form a group. An element of that group is a matrix or a 4-dimensional rotation that acts on the components in reference frame K and produce components in reference frame K prime. So if we have x prime alpha, those are the transformed coordinates, it's given by L acting on the old components. So L is a 4x4 matrix. So for Lorentz boosts in the x direction, we worked out an example before. It was 1, 1, 0, 0, zeros over here, and then here we had something like this. So this is one element of a group, x boost by v, but it's just an example. There's an infinite number of such transformations. So for instance, rotations also form part of that. So if we have a pure rotation, so the time variable is not affected, but for rotation about the z-axis, for example, we'll have cosine phi, sine phi, minus sine phi, cosine phi. So this would be a z rotation by phi. So the boosts are hyperbolic rotations involving the time coordinates. Rotations are of a regular form like that, but there are also various combinations that form a group. You can form products of matrices. So in terms of the generators, 6 generators of this group. There are 3 boosts in the 3 directions and 3 rotations around 3 spatial axes. Now, just as in 3 dimensions, the defining property of a vector was that it was something with components that transform as components of an arrow. We will define 4-dimensional vectors as any combination of 4 numbers, which will denote, similar to x alpha, a alpha, with 4 components, a0, a1, a2, a3, which transform under the Lorentz transformations just as the components of x alpha. So, for example, for this kind of boost in the x direction, the components of a prime will look like gamma a0 minus v over c a1, a prime 1 equals gamma a1 minus v over c a0, and then nothing happens to the y and z components. And just as we did for the x sub alpha, we will also define the covariant components, a sub alpha, by changing the signs for the spatial components and keeping the sign for the time-like component the same. Now, because the transformation preserves the invariant, and the invariant is formed from the components of ct, x, y, and z, in the same way as A is formed from the components of a0, a1, a2, a3, then obviously the contraction defined like this is an invariant, or we can call it a scalar. In 3 dimensions, we use the word scalar to designate a quantity that doesn't change under the rotations. So here in 4 dimensions, in the same way, a scalar is a number that is invariant with respect to the Lorentz transformations. And the contraction a sub alpha, a super alpha, is a scalar. So when we say a contraction, we mean that we sum up the elements according to this notation, but it's a universal convention to just drop the sign of the sum and assume that whenever we have a repeated index, one below, one above, then it means that we're summing up over them. Now, if A alpha and B alpha are both vectors, then because the transformations are linear, then the set of numbers given by the sum of those components is obviously a vector too, just as the product of a vector by a scalar is also a vector. So any linear combinations of vectors are vectors. Now, let's consider a contraction A sub alpha B superscript alpha. Now, this must be a scalar. Why is that? Well, let's consider A alpha plus B alpha, which is a vector, and then contract it with itself. So this is a scalar. It's invariant under Lorentz transformations. But if I open the brackets, I'll find A alpha plus B alpha plus 2A alpha B alpha. Now it's the same thing, so it's still invariant, but then this is invariant because A is a vector, and this is invariant because B is a vector. So then this must be invariant too. So this is invariant. So a contraction over of different vectors gives a scalar. Now, there's another useful form for writing the time-like and space-like components of vectors. So we can write A alpha as A naught, but then you combine all three space-like components in the three-dimensional vector, and we put an arrow on top as usual, and then covariant components correspond to changing the sign in front of that vector. Now, in this notation, we also can write the contraction of two vectors as A naught, B naught, minus A dot B, the usual three-dimensional dot product. Sometimes it's useful to introduce the so-called metric tensor. So we can define a matrix alpha beta with components 1 minus 1 minus 1 minus 1 on the diagonal and zeros elsewhere. And then in this notation, to obtain covariant components of a vector, we can take the contravariant components and then write it like this. So then the index beta in G alpha beta is contracted with the upper beta in A beta. Now, I can also write G with upper indices in the same way, by definition, and then I could write A alpha is G alpha beta A beta. So to get from covariant to contravariant components, we do the same thing. We change the sign for the spatial components, and then it's given by the same matrix. The form of the metric tensor is exactly the same in all reference frames. Now, because A alpha is given by this formula, we can write a contraction with the help of a metric tensor. So we can write it as G alpha beta A alpha B beta, or, which is the same thing, alpha beta A alpha B beta. So generally, we can always, if we have a contraction and one index is below and one above, we can also raise one and lower the other, and we'll get the same thing. Now, let me use this notation to prove a simple statement. The statement that the determinant of any Lorentz transformation matrix is equal to plus or minus 1. So, to see this, let's consider a contraction A alpha times A alpha. We can write it as A alpha G alpha beta A alpha A beta. And now if we interpret this as a matrix and vectors, so G is a matrix, A beta is a column vector, and then A alpha has to be a row vector. So in terms of conventional matrix and vector notation, we can write this as A transpose matrix G times vector A. So here A is a column vector and A transpose is a row vector. Now if we transform to a new reference frame, then by definition A prime is equal to LA. So I don't use any arrows here to designate vectors, but where it's just a letter, it's understood as a vector. Because the contraction is invariant, the A prime alpha contraction with itself has to be equal to A alpha for any L. for any member of the Lorentz group. So then let's write a prime alpha, a prime alpha in the same way. So we can write it as a prime transformed matrix G a prime, and then substitute a prime through LA. Now, a prime transformed is going to be a transformed, L transformed, then we have G, and then a prime, and a prime is just L A. Now, this expression should always be equal to A transformed G A because of this. Because A is now an arbitrary vector, it means that this matrix and this matrix have to be identical. So L transpose G L must be equal to G. Now let's take a determinant of this expression. So a determinant of a transpose of a matrix is always the same as the determinant of the matrix itself. So the determinant of the product of matrices is a product of determinants. So the determinant of G is going to cancel on both sides. So this gives us determinant L squared equals 1, or determinant L equals plus or minus 1. For our example of a boost in the x direction, it's easy to check that the determinant is indeed 1. So if this is our L, so the determinant, let's call it Lx. So the determinant of Lx is gamma squared 1 minus v squared over c squared, which is 1. Now, let me mention a property of the Lorentz group that is useful to bear in mind. So as you see, the group that keeps the interval invariant, so this quantity is invariant, has transformations with whose determinant can be either plus or minus 1. Now, an example of a transformation with a negative determinant would be a transformation where the sign of time is reversed and nothing is done to the spatial coordinates. The determinant of such a transformation, because the matrix simply looks like minus 1, 1, 1, 1, 0, 0, the determinant is minus 1. But this transformation flips the arrow of time. So what was future is now past. But in fact, we just relabel what we call future and past. There's no physical consequence to this. Another transformation that has a negative determinant is a spatial inversion. So a transformation that leaves the time alone but inverts the spatial coordinates. It also has a negative determinant. The whole group, viewed as a manifold, consists of 4 disconnected components. The first component is the one that is continuously connected to the identity transformation, so that you can gradually change the parameters, the rotation angles and the boost velocities, that you continuously generate the transformation from this component from the identity. The second one is continuously connected to the time reversal. So let's call it T. That's the one where you flip the sign of time and you don't do anything with the spatial coordinates. The third connected component is the one that is continuously connected to the inversion operation. So it keeps the time unchanged and changes the sign of r. And the fourth one is the one that's connected to the product of these two. So you switch the sign of time and space. So these four components are disconnected, so you cannot continuously change the parameters and switch from one to the other. The determinant is 1 for the first and fourth components, and it's -1 for the second and third. Now, the one that we'll be dealing with that is relevant to special relativity is the component number 1. There are special names to distinguish these different kinds of transformations. Those that preserve the direction of time are called orthochronous, and those that preserve the orientation of the reference frame are called proper. So number 1, the component number 1 of the Lorentz group includes the orthochronous proper transformations. And this component itself forms a subgroup of the Lorentz group. This subgroup is denoted SO plus 1, 3. S for special, O for orthogonal, plus means orthochronous, and 1 and 3 are the numbers of components that enter with a plus and minus sign in the interval. Now, what do we mean by covariance? Now, what's the point of using vectors, generally speaking? So, in classical mechanics, we are dealing with equations like F equals ma when we write in vector notation, or perhaps the Lorentz Force that we write as E times E plus 1 over C V cross B. So here we write all three components simultaneously in vector form, and we write it in a way that is valid regardless of the reference frame that we pick. If we pick a reference frame, we can project and find the components, but we don't have to. This is a general form that emphasizes frame independence. Now, in relativity, we'll be dealing with Lorentz transformations that involve time and space coordinates. We have found that there is a Lorentz group that leaves the interval invariant, and the postulate of special relativity emphasizes that the laws of physics should be the same no matter what reference frame we choose. So we should seek for frame-independent ways of writing dynamical equations for processes, for interactions and motions in special relativity. So this is why we want to use 4 vectors, like the x alpha that we introduced earlier, so like ct, x, y, and z, but we should seek to find a 4-vector representation of any physical laws that we want to derive. So when we do that, in particular, we'll find that we can write the expression for the Lorentz force, or the equation of motion of a charged particle interacting with the electromagnetic field, in a way that looks like mc d u alpha by the s equals e over c f alpha beta u beta, where u alpha is a 4-vector velocity, ds is the interval, and f alpha beta is a tensor representing the electromagnetic field. So for now I just write it so that you know what we're looking for. We will work out where it comes from, but notice that here everything is written in terms of 4 vectors or tensors, and we have a contraction of one index which turns the transformational properties with respect to those indices into that of a scalar, and what remains is a free index alpha, and it matches on 2 sides of the equations. So this notation is called covariant. We don't have an explicitly chosen reference frame, but we have a notation that can be written in components in any reference frame that we want to choose. So our goal in the following will be to work out the relativistic kinematics and relativistic electrodynamics in the form that can be written in this way. For now, let's derive a couple things that we need for this purpose. So first, of course, we'll be dealing with differential equations. So we need to know how to represent the derivative with respect to time and space in terms of a 4 vector. The simplest thing one can think of is a 4 gradient. So let's take a scalar function. So let's call it phi. And phi is a function of time and space. So we can write phi as a function of x alpha. So x alpha, as you remember, condenses the time and space coordinates. And let's try to write its differential. So the differential is obviously a scalar too. And in terms of the usual rules of calculus, we can write it as d phi over dx alpha dx alpha. So the summation is assumed here, and here it's just a definition of partial derivatives. Now, dx alpha is a 4 vector, a contravariant 4 vector. d phi is a scalar. So in order to make a scalar out of a contraction of a contravariant vector with something else, this something else must be a covariant vector. So d phi by dx alpha is in fact a covariant vector. A good notation for this is to put alpha as a subscript for d alpha phi, and its components are 1 over c d phi by dt, d phi by dx, d phi by dy, and d phi by dz. So this thing transforms as a covariant vector. Now, another thing that we'll need is a definition of a 4 velocity. So I've already mentioned it above. So let's define this quantity. So we want a 4 vector that represents the rate of change of the coordinates. Now, how can I make something like that? I cannot differentiate with respect to time, because time is not a 4 vector. It's frame dependent. I cannot use it in a covariant notation. Now what I can do is take the x alpha vector and differentiate it with respect to ds, where ds is the element of the interval along the world line, and it's proportional to the proper time d tau, as we know. So let's define u alpha as c times this quantity. So ds has a dimension of length, so ds over c is proportional to d tau. It's measured in units of time, so c dx alpha by ds will have units of velocity. Now, ds is c d tau, or c dt square root 1 minus v squared over c squared, as we've learned before. So the components of the Fourier vector u alpha in regular notation will look like c over square root, and then the space-like components look like v, vector v, divided by the square root. So with this definition, u alpha is a contravariant for a vector. Now notice that if we contract u alpha with itself, it's easy to see that we'll just get c squared. So obviously, only 3 of the 4 components of u alpha are independent. After all, there's nothing other than v in its definition, and v has 3 components. So the 4 components of u alpha are related by this constraint. Now we can also define a 4 acceleration. Let's call it w alpha, and we'll find it by differentiating u alpha with respect to d tau again. Now notice that because of this condition, u alpha contracted with itself gives c squared. If we differentiate this expression, the right-hand side will be 0, but the left-hand side will give us twice the contraction of the acceleration with the velocity. So the acceleration, the 4 acceleration contracted to the velocity is 0. So in this 4-dimensional sense, the acceleration is kind of orthogonal to the velocity. In the next segment, we'll see how these ideas of covariance can be used to work out the relativistic equations of mechanics.